focus of this one is on what's needed for generative AI to fulfill its promise in physics. So to start, I'm going to ask each of the panelists to quickly introduce themselves with a few words.
Hi, I'm Dan Huttenlocher. I'm a professor at ECS, and I'm the dean of the Schwarzman College of Computing. I worked on computer vision for about as many decades as you could count. Nobody knew what computer vision was, and have been, more administrating lately, but staying pretty on top of what's going on in generative AI for a lot of reasons.
Hi everyone, I'm Thaler. I'm a faculty here at MIT, and I'm in the Center for Theoretical Physics. That's one hat that I wear, but for the purposes of this panel, I'm representing as director of the NSF Institute for Artificial Intelligence and Fundamental Interactions, which is one of the hosts for this event. I work on theoretical particle physics, and I can even point to the exact kind of year when I went from being a machine learning AI curmudgeon to actually becoming an evangelist. That happened from 2016 to 2017. And now kind of exponential growth in my level of enthusiasm for what these tools might be able to do.
I'm Phil Harrison, one of the organizers here. I was, I'm replacing DJ Reddy, who had emergency issues, so he couldn't come. I'll introduce Vijay because she gets at least an introduction. So he's a professor of computer science at Harvard. He's one of the leaders of the ML-Perf paradigm, in particular looking at ML-Perf for small chips. And the idea here is about building kind of a community of people talking about models in a kind of common language, so that as a whole we can start comparing different models and different ideas together, and then ultimately realize the kind of challenge of problems across domains is actually a common problem and something that we care about. Now, in that context, I am founder of the Fast Machine Learning Group, along with my friend Jan at Fermilab, and we aim to do kind of optimize AI design on chips, particularly for ultra low latencies, for kind of extreme range of processing data at the Large Hadron Collider. But we've come to realize there are many applications, both in low latency AI, but also low power AI. So we now, if you want to run AI to run your pacemaker or your toaster, we have kind of toolkits to do this. And also, I'm a professor of physics here in hydrogen physics and experimentalist on CMS experiments.
All right, so let's start off with a bit of a big picture. We're all here because we see something in the potential of generative AI in the physical sciences. So the question to the panelists is, what is it that you see? What's the thing that excites you about this intersection? Where do you see things going?
Start with some physicists. And I'll build on it.
So when I first got involved in machine learning, I can tell you why I was skeptical. I was skeptical in some ways for some of the reasons that Dave was talking about, that ultimately our goal is to understand the universe, the fundamentals, make inferences about how the universe worked. And it seemed like machine learning methods were just kind of a fancy gussying up of just regular old statistical inference. And it seemed to be actually kind of bad statistical inference, in the sense that you would take these off-the-shelf machine learning models and they wouldn't give you anything like error bars or anything that you could interpret. And indeed, if you really think that what you're trying to do is inference, then I challenge you that maybe you don't actually need fancy machine learning. Maybe there are other better strategies. But part of what changed my mind is that there are certain contexts where it wasn't actually a well-defined inference task for me, where the thing that I was doing was some kind of more type of meta thinking about trying to understand even the structure of the problem that I was trying to deal with. And in that case, if I couldn't really define it as an inference problem to begin with, it was helpful to have this auxiliary toolkit of AI type techniques that gave me new insights on the problems that I had. And so, like as an example of something that turned out to be really valuable for my research is optimal transport theory, which is something that I learned from machine learning world, but I would have never have gotten there directly. Rather, I had to kind of like do this meta thinking about, well, how would a computer think about these problems, and then kind of realize that there's actually this toolkit that can actually do things that I'd never seen before. So with generative AI, it's not so much that I say, oh, yes, that generative AI tool I want to use. Like, it's not like I say, oh, yes, I'm going to take ChatGPT and figure out how to write the laws of physics. It's more of, wait a second, these are computational frameworks that are unfamiliar to me. And man, this seems like there should be something that we can do with it. But again, through the scientific lens. And so, you know, the goal that I would see is that take all the things that we as scientists do, take all of our curmudgeon-y things, before machine learning, I changed my mind, but kind of import them in, things like uncertainty quantification, things like interpretability, but interpretability in kind of a physics space, and see, can you bring those into these really powerful tools? And so I see an opportunity just to kind of leverage those type of new frameworks. It's a new playground and one that I think will bear fruit, but I can't tell you right now, yes, here is what the fruit is that's going to be most useful.
So I got into AI, where do you want to call it? Machine learning? So let me disagree with David. David made the statement that machine learning was not used for individual physics discovery. I worked on the Higgs boson discovery, and we were using machine learning then. The main channel, now arguably, right, there's some, you can go into, there's some details here, but kind of the main, I can point to, you know, if I remove the machine learning algorithms we used at the time, the 5 sigma discovery would have become like 3, right? And I can point to you to various things. And the thing that we were doing at the time that, you know, convinced everybody and allowed us to use this for the Higgs discovery was that we were using it for the instruments, right? There are all these kind of very detailed calibrations that you want to do. And, you know, by then we had already realized that, you know, we could either deploy 1,000 people to do them, or we could just train a neural network to do it. And the kind of low-level maintenance became a lot easier when we made this realization. And, you know, we could kind of simplify problems. And the kind of, you know, low-level use of AI to just kind of machine learning to kind of make things easier is honestly what I have always thought would be useful. The kind of interesting thing now is that the kind of scale of the problems keep getting more and more granular. So before we're just calibrating instruments, now we're kind of asking questions of can we figure out physics processes? And now people are asking the question, can the AI actually point, you know, go out of domain and discover new materials or discover, you know, new fundamental processes, right? So yeah, so that's where I kind of see it growing and evolving. But ultimately, right, it's a tool. I'm a physicist, you know, the AI is interesting, but ultimately we want to get back to the kind of core physics model that we can write down and you know, explain to everybody, right? You know, AI is just a way to kind of save, you know, person power to get there. That's kind of what we.
Super. So I think that I'll stay focused on machine learning for a moment too. I think both of these cases are ones that I view as sort of what I'll call sort of machine learning for interacting with the physical world, right? Which is sort of devices that humans have had to kind of either spit bubblegum together or spend huge amounts of engineering effort on, or both. And then I think there's machine learning for scientific discovery, and I think both of those are relevant to physical sciences and engineering, broadly construed. On the machine learning for interacting with the physical world, I'm going to just pick robotics as an example for a minute, because I think there have been some, in my view, as somebody who has sort of worked at the border of robotics for many decades now, I think there's some stunning changes there. So even in the earlier days of applying machine learning, or even before machine learning, there was a lot of, widespread use of machine learning, there was a lot of focus on AI for robotics at the higher level of things like planning and those kinds of things. What we're seeing recently, and you know, people like Pulkit Agrawal here, actually in this building now, in ECS and CSAIL, he's involved in IAIFI, have demonstrated something that many people thought wasn't going to be possible, or at least not possible for quite a while. So he can now learn controllers that are better than the controllers that humans designed by hand. And this is like low-level control, you know, for example, you know, control for a multi-fingered hand trying to do some sort of compliant motion or control for a cheetah robot trying to, run or, run in circles, which is harder because of the angular motion issues. And people, engineers spend a huge amount of time hand designing those controllers. And now you can do better than the best hand designed controllers with machine learning. That uses simulation, which I think is actually quite interesting. When I think about the physical sciences and engineering, it's often been hard to connect simulation to experiment. And the work that Polkin and others have been doing is they're using, pretty darn good simulators, but not simulators that are, very highly detailed, that you might expect to really be able to run a cheetah robot at the maximum possible speed. And they're able to use the simulation-based training to do almost all of the learning. And then, so, when you think about generative models where you do some fine tuning at the end, the large scale learning that they're doing is all with the sim. And then you do some fine tuning with a fairly small amount of interaction with the real robot. So I think that just has a lot, you all in various parts of experimental physics run some of the craziest devices in the world. And so, I think the human labor to do that isn't really probably interesting from the point of view of most of the science you're trying to do. So I think it's a huge enabler. And I wouldn't have said that as much until about 2 years ago when things like Polkin's work started working, like this fine level, low level devices stuff is really happening now. It's not just, things like path planning for a robot. Then on scientific discovery, so the way I think now, and this is this view I did not have. So I was a little curmudgeonly about AI for scientific discovery until recently. I think it has a lot of other useful applications. But I think what we're seeing now is the ability of machine learning to, I'll describe it in the following way, to reveal the underlying structure of a process that you can't directly observe, just looking at outputs of whatever that structure does in the world. So that, I think the place where that's been most successful recently is biological structures. So probably most of you are aware of AlphaFold, which is the thing that DeepMind did a few years ago, and it's really transformed large parts of biology because you now can do reasonable protein folding on almost any amino acid sequence as long as you can get a reasonable multi-sequence alignment of it to other known proteins. But what a guy named Alex Reeves and a team at Meta did over the last 2 years or so, is they use things that look very similar to just completely vanilla transformer style autoencoders like are used for learning natural language, purely on amino acid sequences. Nothing, and so you can think of the set of amino acid sequences that occur in the real world as some output of some unobservable process about what kinds of proteins actually exist in the world. Very unobservable, very complicated process. You can think about the surface of natural language as some observable output of, again, some very complicated process that involves human brains, human social interaction, all kinds of other things. And in both of those cases now, very different domains, they're able to recover things that, linguists would have thought took, a lot of thinking about models of language at various levels, or that biologists would have thought really took thinking about, sort of 3D structures and how proteins dock and so on and so forth. So I think there's a broader principle here that and in a lot of science, we have data that's the output of some unobservable process. And I actually think that these models now are very worth trying on those kinds of problems. So those are the two that I would throw out, and I'm happy to get pushback on them, et cetera.
Thank you. So you all have perspectives as the leaders of colleges and institutes on sort of the community building up at this, in some ways, interdisciplinary intersection of science and AI and computing. And we're interested in what you see as being needed from the community perspective to really exploit all of the developments at this intersection. Where are we and where do we need to go?
I mean, I can comment.
Okay, well, I can comment, but again, I think I'm better in response to what you guys say, since.
All right, sure.
Well,
I have a very strong opinion here. So we basically heard the word CNN many times today. And part of the reason we heard CNN many times is because, it's a great architecture that understands images. Where did CNNs come from? Well, arguably, they came from the ImageNet challenge, right? They came from a data set of basically cats and dogs and humans. There's like 30 different dog breeds in the image. But it's a nice labeled data set that allows you to kind of systematically go through and solve the image recognition problem. And ultimately, things like ResNet and CNN, AlexNet, like all these kind of architectures that the whole AI community now knows came out of this one data set challenge. The problem is that that's just one problem, and there are many, many, many really interesting problems that machine learning and AI could stand to play an important role. And I think as a community, if we want to bring awareness to this, we need to start bringing data sets, challenges, and making it clear to the community that there's not just one problem, there's many problems, and there's kind of a diversity of applications. And I know there's always the kind of brightest problem in the world. I think there's this large language model problem people are trying to solve now. But I think that's kind of it's not helping the field. It's kind of making the kind of AI world a little bit too narrow. And I think some effort needs to be to kind of going to the community and making it clear that there's not just we're not just going to solve protein folding problems. A bunch of these very complex high level problems. There are many other interesting problems, and the impact of these problems is potentially even bigger than some of the problems that people are just obsessed with. So I really think challenges. By the way, this is why I asked BJ to come here, because I wanted him to talk about this. But
you can channel him.
yeah, but the point being is that challenges and building a variety of challenges and making this clear to the community that there's lots of different kind of interesting problems is something that we need to highlight more, and it's something that I don't think the community has done the greatest job at for that.
So I totally agree. And I have some notes here of some things I wanted to say. And one of them was, making sure that as a community, we have the right definitions of success, communicating what that is, and challenges are a great way of doing that so that people have common goals to tackle. And the challenges, again, need to be diverse, and they need to be actually useful ones. So we need to have, for example, challenges associated with instrument calibration, where like, what is the definition of success? What does performance mean? It's maybe different than the type of performance that you would have for a classification task. So I want to say a few other things. So one thing the community needs is just in general sustained funding. And the community also needs career pathways. And so, of course, being the director of an NSF institute at the time, advocating at the federal levels to continue funding for this type of work. Then we have these fantastic IAIFI postdoctoral fellows. Hopefully they'll get awesome jobs in academia and industry. But part of those career pathways and part of that sustained funding is making sure that those of us who are working in kind of specific domains or have domain expertise, that we're somehow able to communicate what we're doing and the value and the interest in what we're doing to an audience that's not necessarily expert in our particular area. So if you have a CAGO competition related to the Higgs boson, you don't need to know anything about the Higgs boson, but nevertheless be able to tackle that data set. And if it's an intriguing enough problem, then people might embrace it, regardless of whether they know the technical details. And I remember this experience that really hurt me, but then I realized that kind of it made sense. I was working with Google Accelerated Sciences on a problem, and they kind of fired me. And I said, "What are you talking about? We were making progress." And they said, "Jesse, you know too much about your problem. How can I contribute?" And indeed, like thinking about, well, what is a type of problem that is interesting from the scientific discovery perspective, but also interesting to people who are maybe not experts in that particular scientific domain. Competition is certainly one way to do that. And then one other thing just to highlight, which is maybe more specific to the people who are doing IAIFI work than the physical sciences more generally. Scientific discovery is actually a pretty big umbrella that includes things that are more on the application-based side, where you find one material and you're super happy. And that one object is something interesting, something you can test. But then there's the more curiosity-driven side, where it's more about inference about how the universe works. And there, it's a different set of goals. And sometimes that one can be the one that's hardest to communicate to people, that it's not about understanding one material. As a fundamental physicist, I would want to understand all the materials and the statistical properties of all those materials. That's not as useful on the application side, but nevertheless is a part of that scientific discovery process. And so, competitions, staying community, but then also understanding that there's a continuum between things that are applied and things that are more curiosity driven. That's what needed to have a vibrant community overall.
Super, thanks. So I would point at some communities that now I think have kind of established, they're looking at problems that are not the conventional machine learning problems. And it's really weird to me as a computer vision person from, back when the original perceptron models existed and, just didn't work all that well for a lot of reasons. The huge role that computer vision has played in development of convolutional neural networks, deep learning generally, use of autoencoders in the language world proved to be a good place to apply those, but they were developed earlier in machine learning in vision. And I think part of it is because it's a very complex set of data. I mean, you have the images of stuff on Earth, stuff, it's very complicated sort of input domain, and one that lots of people create images in. But what we're starting to see now is that in addition to sort of images and language and video, there are getting to be other subcommunities, and they're sometimes organized around particular kinds of challenges that could be useful, and sometimes they just sort of evolved out of just problem domains that have been amenable to not just use of machine learning, but to use of machine learning that informs the machine learning community about the next set of algorithmic advances that they should make. And so I certainly wouldn't have predicted this a few years ago, but there's a pretty active subgroup of people working on sort of chemistry and chemical engineering and machine learning. There are regular workshops at NeurIPS and ICML and a bunch of papers in the main conferences there now around chemical discovery and chemical synthesis, which is actually quite different than discovery. You can discover something that you can't actually synthesize very well. And those are involving, chemists and chemical engineers and people who would call themselves machine learning people. So it's sort of starting to create communities at the boundary that aren't, the computer vision and natural language communities were largely computer scientists to begin with anyway. They were a little broader than that. Computer vision, I would say, was probably, 1/3 non-CS people and 2/3 CS people. That still made them very dominant community. People interested in chemistry and chemical engineering are quite disjoint from computer science, and it's become a big, not big, but significant subcommunity. And then there is the biological community, particularly focused on sequence data, which has gotten to be a sort of significant subcommunity. And part of it is that those problem domains have been driving additional approaches. And I think that's happening in robotics now too, which I view robotics as really behind the rest of in terms of the use of machine learning compared to language processing or vision. And I think that catch up is going to happen very quickly now. So those problem domains are starting to get to be amenable to machine learning techniques. So I think, propose a workshop at NeurIPS or ICML, see who shows up, right? I mean, I think those are good things to be doing. Maybe you already are.
Yes. So there's the last semester, there's two of them. There's the machine learning and the physical sciences, and sorry, what's the other one called? AI for science from something.
Yeah, that
like
was so broad, though.
Yeah.
I think AI for science as a, like, we can all think about it at the level of genes is a good thing. But the real work still really happens. It may not be a single discipline, like I think chemistry and chemical engineering has actually been very productive in the machine learning domain, exactly for some of the kinds of reasons Jesse mentioned, which is that some of these are things where you want to be looking at really specific applied outcomes, but they can have broader, more general implications. So I think the chemistry plus chemical engineering has done a pretty good job of combining some of those.
Yeah, so I'll just second, as somebody who wrote a NeurIPS application for a workshop and got rejected. I mean, I can say, so.
You're not alone, even with people like in the, I mean, it's just NeurIPS is so
Yeah,
competitive for
I know
everything.
I'm not, I'm not, I don't feel bad. I don't, I still sleep well at night.
Good.
But, I mean, the concern that we always had, and things like AI for science and machine learning for physical sciences, is that, they're too broad, right? You really need a very targeted application. And, we built this fast machine learning community, which is like roughly 1,000 people now. Out of a very specific use cases that, GPUs and current processor technology cannot run things fast, right? There's a kind of a threshold. You can only process data so quickly, and you need to go beyond that for various reasons and various use cases. Because we have this one single idea that you can kind of explain in a sentence, you can kind of translate this and build a community. And, kind of by virtue of doing this, we've been able to attract a lot of people from a lot of different scientific domains. I personally think that in physics, we failed to do this so far. I don't think we have unifying ideas, and I don't know if we do. I certainly think there are a bunch of really good ideas in physics that could become elevated to, like, this is a problem we could all team up on and focus, and this would lead to major discovery. And I think there are a bunch of these ideas, but I think us as a community have not cultivated this. Maybe this white paper is a way to help push us forward.
Okay, so I'd like to come back to a couple of the things you all touched on in your answers. We'll start with one of them, which is, what do you see as the changing role as industry continues to develop? There's big players, there's small players, there's startups, how that interfaces with the academic efforts, and what do we need to do as a community to really leverage connections there?
That's right.
I mean, I think, a bunch of people have raised this today, is that some of the problems with solutions we saw here cost more than, the budget, the operating budget of, like the whole physics department at MIT, right? And, certainly, if you summed all the grants, right, the kind of computing costs that you need for some of these solutions is just outrageous. And that's not to say that we can't do this on a smaller scale. That means we need to be aware of, share resources, and come up with a way to kind of engage the community, because it's not just, these things cost a lot for, a short period of time, but, the resources can be shared. There's interest from the kind of whole scientific community to share these resources. So I think there's an opportunity to engage people. But I think the kind of important thing is that if you want to engage these people, you have to make it clear to industry or, donor, I don't know, like universities, whatever, that, the government, that the problems that we're solving have kind of a broad range of downstream applications that can be used, for ideas that, we had not. And sometimes this messaging gets lost when we're so focused on the science. But ultimately, the kind of cost of these things is, more than the cost of the fields of science that we work on. So I think we'll need to be cognizant.
So in terms of the size and the cost of models, I have the dream that it will be folks in the physics community who think about emergent phenomena will come up with actually the much cheaper version of these various models that are actually more energy efficient. You can actually run on your laptop, things like that. So maybe it's our community that will be forced, both because we have the physics knowledge about emergent systems, but also the necessity to have things that can be scaled down, and we need to develop those tools. But indeed, right now, that's not the direction that things are going. But that's maybe optimism, but that doesn't kind of address part of the question, which is, we want to engage with industry. And I would say that my personal experience, this Google Accelerated Sciences case that I mentioned before, that was my fault. I didn't explain very well actually why it should have been interesting for them, and I'm much smarter now about that. Now what I see is that there actually are people in industry who are super enthusiastic to work on academic problems, and finding that shared dialogue is there. But then things get shut down for various reasons, and so let me not use names. But I was kind of shocked to learn at NeurIPS last year, someone who I respect very much, who works in industry, who had a 4+1 arrangement, 4 days at a company, 1 day to do academic work, and that company took back that 1 day, and that person then left that company. But say, wait a second, the profit motive or profit incentive or intellectual property is going, in some sense, in the wrong direction. And finding people who within industry who are able to do this type of collaboration just seems challenging. And what I'm really hoping is that when Dan gets the microphone, that he'll explain how we can have fantastic academic industry partnerships, because I see this willingness to engage. But at the same time, I'm seeing that the types of papers that were coming out from my friends who are working in companies, they're not putting those papers out anymore. And things are kind of getting closed down in a way which, again, maybe it's a temporary trend, but certainly gets in the way of having interesting dialogue and collaboration.
So I'm going to take a really long view on this because I'm old. So I've watched several cycles of sort of boom and bust. You can call them AI winters and whatever else you want to call them, where companies have sort of invested in a very broad range of problems in the tech industry, and then where they've kind of pulled up the drawbridges and narrowed. This is a kind of weird one because it's not like the industry's doing badly. Those are the previous times. It's that they're all so obsessed with these large models for language and images and video that they're just pouring so much resource in there, they're shutting everything else down. I think the things that I've learned, and I've spent a fair amount of my career actually not in academia, is that it's important to try to forge some kind of broader strategic interest between academics and companies that can survive the ups and downs of that, and recognizing that the spigot's going to go get more open and more closed over time. But if you've identified some longer term objectives that you share, you can kind of make it through those periods. And I've had some of those in my own kind of personal research career. I've aimed to build some of those while I've been here at MIT as a dean, and did them in my previous academic administrative kind of roles. But the objectives are just different. So you have to figure out, how is the sort of corporate objective, which at some level is profits. I mean, in the end, that's the objective. But profits means a lot of things, right? I mean, it can mean we want a halo to our, brand and our expertise in this area by engaging in, amazing basic work with people who don't work at our company. I mean, profit is not always, except in certain times of exigency, maximizing the, sort of percentage of income that turns into profit. It's a much more complicated thing than that. It's also getting companies to understand that their long-term talent pipeline depends on certain kinds of relationships with academia. And I think that way, a lot of physicists don't end up doing physics. They end up doing things that companies that aren't doing physics still care about. So I think there are those kinds of opportunities with companies to forge those where, there are problems physicists look at that, do challenge the core kind of things that the company is doing in ways that are interesting to them in good times. And even in less good times, they still want to be able to hire students who come through those kinds of programs. But, it takes like a good piece of advice I got way back when I started raising money as a dean, and I think it's very applicable in these kinds of settings with, kind of centers and other academic things is, ask for money, get advice, ask for advice, get money. It just, I think, and companies tend to be transactional, so if we just, again, because it's the nature of what they are, if we get transactional and sort of just focus on money at the beginning, you can't really build those longer term relationships. You have to look at the beginning of what's the interaction, probably has relatively little financial return to it. And build up those engagements, and then, and have to understand how to do that in a way that makes sense for all of us with finite time and everything else. But I do think, more senior faculty can, hopefully carve some time out, especially ones who are in roles running something, in ways that can, help them. Well, I mean, it's all of us, we're all not junior up here.
No, he's not yet, but
I'm close.
You're close, so I thought you were,
No,
okay, so.
sorry.
And why are you spending your time, no.
I was forced to look at it.
Building data challenges. But no, kidding. But I think, yeah, it takes a different mindset than saying I'm going out to find money.
Okay, so I was gonna leave the elephant in the room to the end, but we've been touching on it, computing. Everything we've been discussing requires computing. The community of people who want to use computing is growing. The computational needs of the tools we're using are growing. Access to computing in the academic sphere is not growing as fast.
I'll take that one first. So a few things. One, the same thing's happening to all of our peers in doing basic research in industry. Bill Freeman was here and left. He spends most of his time at Google, and so, spends like a day or two at MIT. They have less, the Google scientists who are not working on Google's large language model, public priorities, have less access to compute than we do. And for them, it's a huge shift because they were used to having, huge access to compute. I guess I'm a firm believer in the fact that necessity is the mother of invention. And so I wanted to sort of stress something that Jesse said, which is that for the good of the world, we have to not be spending this much compute resource on the kinds of problems we want to solve. The aggregate power usage is becoming an embarrassment. And I think that these are things that we can and should be working on in academia. Look at the use of diffusion models in computer vision, and I mean, that's physics. I mean, it's the kind of simulations you all have done for a really long time. And, like way back when I worked on computer vision stuff and low-level segmentation, I mean, things like icing models and stuff that you were all very familiar with were also things that we were very familiar with and working on for different reasons because of the value that they have in thinking about, spatial arrangements of all kinds of stuff, not just what you all look at. So I do think there are real places for physicists to make contributions to those kinds of fundamental computational algorithmic advances that are going to have to be made. And so I think that's a challenge I would throw down. I don't think it's just a challenge that's going to get solved by, computer scientists, electrical engineers, and the kind of people who have classically been building computing hardware and algorithms in, for the last few decades. Quantum's floating out there too. We'll sort of see. Doesn't necessarily look like it's going to be super low energy. We'll see. But there's stuff we really have to do on both the hardware and algorithms front. That said, those of you who want to solve some other problem, that's a pretty unsatisfactory answer. So let me try to also just say that at the federal government level, at the university level, at university sort of consortium level, individual departments, collections of faculty, there is a lot of investment in computing. Peter Fisher's sort of taken on the task for MIT of trying to help people be able to share better than they might on their own, exactly for the reasons that the peak applications of these things are often bigger than what you're gonna run, you know, for long time periods. But there's no single magic answer. Everybody I know is, you know, struggling to piece together the resources. I would just point at one other funny thing, and maybe it's related to funny meaning odd and not amusing. So in the past year, we hired 3 people from Meta as faculty here. So it's not that there's some, you know, gigantic, you know, like the world thinks there's a sort of sucking sound from, and these are all AI people, right? Machine learning people. Some people want to work on problems that are better studied in an academic domain, you know, maybe because Meta or Google decided to stop funding that kind of work, but not always. You know, some of them are sort of fundamental ML people who are very valuable in industry, but think that some of the problems here that industry doesn't want to work on are the best way to make progress on what they want to do. So I find that interesting. I think it's always easy to complain about what we don't have. It's interesting to watch people who sort of are coming here for what we do have, and we might have thought that they're the ones who have what we need. So that would be my more philosophical answer there.
All right. I guess, so I don't see Greg in here. I hope he's not connected. So he gave a talk. I mean, I want to use him as an example. So he said he trained a 640 million parameter with 40 million inputs. His data set's smaller than his model. And he's like, oh yeah, it's extremely unconstrained. That is a luxury that I don't know we're all going to have in the future, right? You can't just throw the giant largest model and, you know, giant computing cluster. He's working at Microsoft. I'm sure he has access to ridiculous amount of compute. This kind of luxury is something that I think people are not cognizant of in general. Computing is something, we've heard about symmetries, we've heard about ways to kind of compress the problem, condense it to something that is scientifically meaningful. This applies generically to computing. And this is something that physicists actually have potential to play a major role in, because there is, like a lot of experience dealing with, complex data sets that can be reduced, using kind of fundamental arguments, right? So the other thing to say, kind of related to that, is that you don't need a 650 million model to solve most of your, like 99% of your problems, right? And I see this over and over again. People just put these under constrained models. They solve their problems. Say, great, machine learning is the best. Let's move on. But I see this kind of, at many levels, and I see this also now. We're trying to kind of, so at the Large Hadron Collider, we're trying to kind of integrate now the new GPU computing clusters. And we often see that there's just people are building these giant computing clusters because they see some motivation, but we often see that the resources are not actually kind of balanced for the problems that we care about. And people are just kind of abusing the resources, right? They're like, oh, let's just submit jobs that use a GPU, but then you look at GPUs, it's just only like 1 or 2%, right? And I see this time and time again, when people are just abusing compute resources. And I think that there needs to be a little bit like some kind of serious thought about how to use these things efficiently, how to think about, model compression and, understanding, when machine learning is necessary, and when, like when you're just being sloppy and just throwing kind of under constrained models and everything. The reality is that when you start doing kind of big, major scientific experiments, this computing is a limited resource, and it's something that we often don't, we take for granted. And I think, I see this like quite often that people they're not aware of. This is something that we should kind of just bring more awareness to, because I think there's a lot of these things can be solved very kind of quickly and simply just by thinking a little more about the problems you're trying to solve, and not just trying to kind of, plug in the latest, greatest thing, that takes even more compute. So, I mean, yes, there's going to be more compute around, but I think the kind of demand and the problems growing that faster than the compute. Something that I think there's a potential to kind of set examples or kind of deal with kind of problems, bring kind of new ideas to these problems that really, benefit from the larger scale.
So let me just say something from the kind of the NSF AI Institute's perspective. This issue of compute is understood to be a problem. It's not understood what the solution is. And then you're mentioning, there's actually a lot of different investments, but they're kind of small investments, kind of piecemeal. And unfortunately, they're all on kind of different platforms with different type of interfaces. And with my graduate students who got me into machine learning, I can't remember how many times they had to port their code from one thing to another. Go from Azure.
Gen AI will help with that.
There you go.
Porting code should be done by machines almost any day now.
Please, I would love that. And if you can get the tables to line up in the right way on my LaTeX documents, I'll also do it. So but one of the things that just kind of pointing out, so just kind of the things that are happening, and maybe just to give you a sense that there's a lot of things happening. It may not be all going in the right direction. I don't know what model's going to work. So within NSF, there was a compute infrastructure called Exceed that was now been replaced with something called Access. And my understanding is that Access is easier to access. At the same time, there's another pilot that's going on, the National AI Research Resource Pilot, which is another source of compute. I don't really understand how that does or does not interface with Access. And then, even on campus here, you mentioned Peter Fisher and Orchid, trying to figure out how to bring everything together. But I'm going to actually be having a conversation with Peter and someone from Amazon Web Services on Monday. And I think we need to recognize that academia is a particularly hard area to serve because we have so many different platforms individually. It's not like you convince me that, oh yes, this platform is good, and I can immediately convince Fiala, yes, you can run your code on that platform. Like, absolutely not, and vice versa. Though actually, if you can run your code, probably I can do anything. But I think that's a challenge for some of these cloud providers is that they trying to engage with the university with this very heterogeneous computing culture. That's challenging. And the comment was that it's much easier for a cloud provider to interface with the national lab than it is to interface with the university, because at least the national lab there's a sense of better kind of controlled infrastructure. And then there's things like security is a big issue. Just universities, since that's difficult to deal with in that sense. But anyway, there's a lot of things going on. It's a frustration that I know a lot of people have. There's an awareness of it, and I don't have answers.
I also don't have answers, but I do think it's getting somewhat better. The NAIRR that you meant, the NAIRR which you mentioned is it's an outgrowth of an effort by a number of universities to try to get Congress to pay attention to this problem. It's not, the funding for it's only partially authorized, but the idea is to do some things at some significant scale. Outside of NSF often has a hard time doing things at scale, right? They have a sort of mandate to spread the peanut butter around, so to speak. So I think DOE may also end up being part of NAIRR because they're more used to doing things at scale. But the aim is to try to produce systems that people can use, but it's going to be standard systems of some kind. So they're going to have to adapt or port from whatever their favorite toy in their lab is to something that's bigger scale than they probably can afford to put together with their regular federal funding.
I kind of want to comment about this because I disagree with some of the stuff you said, Jesse, because having spent more money than any other professor in the cloud at MIT, like they had to renegotiate Google Cloud's contract because of me. So because of that, the experience I got actually in the cloud, and then I've done kind of actually equivalent national lab work. In fact, we had the national lab compute facilities talking to the cloud and spending ridiculous amounts of money. The national labs are not very good. They're not efficient. They're not useful. They're not well useful because there's this huge emphasis in supporting kind of open source software in the infrastructure. And the cloud providers have actually had the problem that you say universities that they haven't addressed is that they have a lot of diverse users, right? And the kind of balancing of resources and the scale that they've done this is at a level that I honestly don't, national labs have done, and I don't think that universities have done, and I think they actually have, like, the toolkit, my experience in the cloud is actually fantastic. And I honestly think that, kind of bringing the ideas that we learned from the cloud to labs is great. The Narrative pilot came out of, part of it came out of the NRP, the National Research Platform. The National Research Platform, I helped kind of with the ideas of this. It builds on ideas coming from actually the cloud. It doesn't come from other national labs. It uses kind of the toolkit and the distributed toolkit that's actually really kind of useful in terms of integrating and building kind of diverse computing environment. I think the Narrative pilot and the idea of growing this is actually the kind of mentality they have. And there's going to be a workshop next week in San Diego if you want to comment on this. There's kind of an emphasis here to actually bring a lot of the ideas that industry's doing. And part of, I think, the success of these large language models is because they've already thought about this problem. And I think, in general, that there's actually a lot to be learned for computing infrastructure from the cloud and from kind of the way people have thought about this in terms of large scale industry services.
Yeah, so what I would just say on this is I agree with you. I think the challenge of most of the computing infrastructure historically in national labs is it's still modeled on the high performance computing sort of model of things, which has a harder time really scaling, just given the nature of that hardware. That's, I think, also a big problem in addition to sort of the maturity of the software. The cloud was designed both hardware and software to essentially scale arbitrarily. The cost of that is the interconnect is less dense on a shared memory multiprocessor machine. But what we're getting with the GPU sort of clusters is sort of an interesting mix of those two models. So, you get a bunch of NVIDIA cards on a shared memory with extremely dense interconnectivity, but then they're in a cloud provider connected in a lower density high-speed network, which is kind of an interesting weird hybrid of that. So the nodes get super capable. But again, there's this huge limit on what an individual can scale to.
Oh, just to say, I certainly do want to imply that the national labs had a good computing infrastructure. I was more thinking about if you're a vendor and you're trying to interface with an entity and trying to provide a product, at least this is what was told to me, is that it's harder on a campus that has such different use cases versus a national lab where I think there's more centralized use cases, so that external vendors come. But your experience is different.
No, I mean, you talk that the national labs kind of over design their computing clusters for things like LinusQCD, sorry, and they're not useful. The national labs are not useful for other problems, and in fact their compute's not very heavily used right now because of this. This is an anonymous comment from a national lab compute supervisor.
We can talk about that later, but there's other reasons for that.
Oh.
But okay, all three of you have touched on different ways on our community literacy and our workforce. So Phil mentioned we can use resources more efficiently. That's something to do with the literacy of our community in high performance computing and computing in general. Jesse mentioned having pipelines for people to continue their careers. Dan mentioned pulling people back out of industry. So I'm interested in all of your thoughts on our community literacy and our workforce development opportunities and challenges on that front.
All right, I'm going to make a politically incorrect comment. I think both physics and computer science, each individually in this field, think that they can solve every problem in the world alone. And this is actually a place where I think the field's finding better ways to collaborate. And that's why, I cited about what Jesse's been doing. It's going to be, it's the time. And I don't have an answer about how to do that. But I do have some sort of cautions about what it can't be to work. In order to work, it can't be field X in service of field Y. Doesn't work, like academics don't, we're not here to just be the service department for another field. And that could go either way in this. I'm not saying it's like CS and service of physics. I can imagine scenarios in both directions. Instead, what we need to do is spend enough time together, and that's what I think in some ways IAIFI's been doing, but it takes more than that. In small groups, thinking about the kinds of things where there actually could be some mutual interest. And then the work in doing that, I think, does start to build other connections and build paths to increased computing literacy in sort of advanced algorithms and computing literacy in physics beyond the kinds of algorithms you all naturally think of. I mean, there are physics algorithms that physicists have developed that are more sophisticated than what computer scientists do. I can tell you as a computer vision person, one of my biggest frustrations with graduate students is that the CS students didn't know enough math and enough, sort of physically based algorithms, and the students from electrical engineering or physics who worked on these problems didn't know enough computing. And it really took a mix of those two. But I think we need to find problem domains where it makes some sense to start to work together, and that will develop mutually agreeable ways of doing things educationally. And then I'll point at Mike for a minute. So I guess, well, one thing that we are doing in the college, which would be great to just put some effort into physics and some people in the UCS thinking together, which is the common ground for computing education, which Mike serves on, where we're looking to try to find multi-departmental collaborations towards developing, this is both at the undergrad and graduate level, classes that teach what I would call broadly applicable computing. The problem I see that we're in right now as a world is that in most fields, the computing that gets taught there, for obvious reasons, is mainly aimed at problems in that field because people are interested in the field. Computer science is this bizarre field that's interested in computing broadly everywhere, but then not that tied to individual domains. And so the aim of the common ground is to really tightly couple disciplines and broadly applicable computing with each other, which doesn't naturally happen in the department structure. As in a department outside CS, it's focused on the department. At CS, it's not focused on any problem domain at all. So how do we bring those together in an educational way? So we have something at MIT that's trying to start to do that. There are some success cases, none with physics yet. I would love to see some.
What? Oh, no.
And Mike should call my bullshit.
So in terms of the kind of win-win between communities, as IAIFI director, it's been wonderful to see these happen on kind of one-on-one exchanges. So you mentioned people coming from industry. So I had a fantastic conversation with Pam and Lee about AI plus science, and that was really fun and really looking forward to him coming. And there needs to be ambassadors between the various disciplines and build those bridges and connections. And certainly, and personally, I have a really fun collaboration with Dava Ba, who is at Harvard, and talking to someone who's thinking about computational neuroscience, someone like me thinking about particle physics, and realizing that secretly we're working on the same problem. Like that's really exciting, and I think it's a win-win and a great dialogue. Internally within physics, I would say that there's also a need to broaden our thinking a little bit. So one of the things that Mike and I did was to start this interdisciplinary PhD program in physics, statistics, and data science, and actually have a verifiable credential that has that kind of cross-disciplinary expertise. And one of the things that Bill has done is bring into the physics department a course on computational data science and physics. But in both of those cases, there is pushback from the physics community saying, wait a second, you're bringing in this new toolkit. Physics is not about the methods. Physics is about the domain problems. And a really interesting conversation that we need to have with our own faculty. Specifically for Common Ground, I think this is just a case of the timing was off because Phil's class is like a perfect Common Ground opportunity. But we just got it approved as part of the physics, it's a breadth requirement now.
Just not like this year.
Yeah, this year. So finally, right? And so then, but I think, the core there, it's based on in this modular way where you have science paired up with technique, but those things can be separated and moved around in some really exciting modular ways. So I see a lot of opportunities in that direction. And indeed, at some level, given the research that I'm doing right now, oftentimes I can have a more interesting, vibrant conversation with other people, let's say the MIT Statistics and Data Science Center, than I can with my physics colleagues, because actually there is shared data structures or shared data problems. And it's actually really amazing to me the way that computation plus statistics and data science like that actually, it's a language that as long as we get our vocabularies to align up, it is a language that we can share across domains.
Yeah, I was gonna say there's not a common vernacular, and there should be, and it's, I think once you have that common vernacular, then, people will realize that there's a huge overlap. Some of the things that, I honestly don't know why physicists don't, struggle with statistics and data science being such a core component of so much physics that people struggle that this is, with this idea of being in physics. I think this is something the community just needs to realize. The people who are, don't realize this need to retire. I think it's just an evolution of the way things are going. But the one thing I will say is that when putting together this class, there were certain statistical things that physicists are obsessed with, right? Things like hypothesis testing and also common parameter estimation, that the computer science community is like aware of and kind of teaches, but they're not the same obsession. And I think there could be there's a room for kind of community of merging fields, where I think you could play, what we've learned, because in things like hypothesis testing, I know we've kind of gone way deeper than the statistics community there, but the statistics community has all these kind of brilliant ideas to kind of expand the kind of scope of what could be done. And I think there's a room to make a kind of subfield that UNICEF do. And it would be a dream if MIT was a leader of this kind of transition.
So I just wanted to speak to this issue that Jesse raised about, and I guess you also touched on, it's very hard to take this kind of educational change back into the graduate or undergraduate curriculum and give it part because the curriculum's full. Like, what are you taking out, right? And so, one thing is to try to integrate it in ways that you don't have to take something out, but again, if it's yet another methodology, what other methodologies are going on, this is just fundamentally hard. It just, it takes time. But we're doing it with departments like political science now, we're a lot further away than physics is. It just, but it is not, it's true in every department. It's not a physics issue, is all I wanted to say.
Okay, so I also want to make sure we leave time before closing questions for you to add anything. I see Jesse had lots of notes.
No, sure. I have a couple of things to say, but I'm also curious if there's questions in the audience. But I can tell you there's only one bullet point that I have.
Good people.
Okay, so this is something that I don't have an answer to, but I'm curious what people think about. And this came up in a conversation about, could academia ever compete with industry on something? And could you ever get a community of like-minded people to pool their resources to do something? And here's the fundamental question, which I don't know for our fields going forward. is the thing that we need to cultivate more collaboration. There's an entity called the Trillion Parameter Consortium that's trying to bring a bunch of people together in order to think about, let's say, foundation models at a big scale. The Trillion Parameter Consortium, despite its name, you might think it would have some resources. It has $0. So trillion parameters with $0. So it's aspirational, but that's an aspiration to build collaborative infrastructure. Is that what we need, or is what we need competition? And of course, coming from the particle physics community, we've seen the great things that can happen when you have teams of people who collaborate but then compete with each other. But I don't know which of those models is really what we need for this community, because you want to be a welcoming place that you can bring in newcomers, but also you have to have something that will, for example, keep model size down or performance going up or things like that. And that's something that I don't know the answer to for this area.
So I think you need to collaborate on infrastructure, and you need a shared vision of what infrastructure is going to drive the science forward. But then I do think that science is better done in small teams than huge teams in most cases. I actually think physicists do better than any field at this set of issues, experimental physics, and not just in particle physics. There's a lot of big, expensive infrastructure in physics. But I think it's a mistake to try to build infrastructure that competes with what industry is doing. And generally, physics is quite good at defining important infrastructure to making fundamental scientific progress. I'm sure inside your field, it feels like there's never enough, but if you look at it from outside, I actually think you're better than most other fields at identifying infrastructure that people can sign up to, whether that's, space telescopes, ground telescopes, gravitational wave measurements, particle physics, and there's a lot of infrastructure there, and it's distinct from what is being built in industry. What worries me about the Trillion sort of parameter consortium is that's just head-on competing with industry, which is just going to throw more money at it, at least while they think they can make money there. If they start deciding that that huge capex is not going to yield return, believe me, they will stop buying all that stuff. But at the moment, that the belief is that they can't not be in lead, at least for a handful of companies. So I wouldn't aim to compete with it directly, but I think shared infrastructure is super important.
I'll disagree with everybody and say that the precepts that we did when we founded FastML and then ultimately E3 Institute and a few other things that we've done, the precept is that we don't want to compete. And you can argue and discuss with your colleagues, but trying to have multiple groups compete when there's limited resources. And honestly, this is what we see at the LHC. I think honestly we could merge the collaboration. I don't think this kind of need for competition is there. And I think the bigger competition is the science itself. You want to compete with the science. You shouldn't be competing with each other. And I think it's unhealthy to make small groups. I think the bigger, as long as, now part of this means that you also have to be able to respect each other and respectfully disagree with each other, which is not something that everybody does. And there are kind of ways to do this and handle this in like large collaborative environments. But I honestly think that us trying to compete with each other inside a field as small as physics is not something that's.
Any questions from the room?
Or comments?
Well, I always have things to say. I have so many things to say of the things that came up. There's so many good ideas in here. But I just want to say one thing that I encounter a lot, we think about a lot at NYU and have failed to solve is, so some of the most interesting things that have happened at NYU have been when two faculty members from different departments co-advise a graduate student or a postdoc. Co-advising, like almost everything I've done that's interdisciplinary with statistics or math, computer science has been through co-advising. And this sounds so trivial. It seems like such a trivial point, but it's actually really hard to co-advise at NYU because there's a funding question. If I spend money on a graduate student in computer science, physics will put my head on a pike. Like we are all funding is. I mean, it's very hard to share resources across departments. And at NYU, it's so complicated because they're actually different schools. And so if I work with someone in medical school or in Vermont or in statistics actually is in a different school again. And so there are just purely accounting administrative things that happen at the university that stop us from creating the best environments we can create. Maybe MIT is much better.
Sadly, no. So, but I can tell you, so I'm proud in general of what we've done in IAIFI, but I think one of the things that we didn't think through was precisely this issue of money at the graduate level. At the postdoctoral level, our IAIFI fellows, many of them in this room, they come from many different fields. They can work at MIT, Harvard, Northeastern Tufts. Within MIT, they can have their feet wherever they want to be. They can do those collaborations at the postdoctoral level, in part because postdocs are more independent. They can build those collaborations, but at the grad student level, the way that we allocated funding was attached to a faculty member. We're thinking about renewal within IAIFI, and one of the recommendations from a kind of committee that we put together to give us suggestions about what you might want to change was indeed the idea that you would have some level of grad student funding on an NSF funded grants, which kind of solves a little bit of the question of who owns it, but then that you could allow that to be kind of not directly attached to one faculty member. And indeed, you can imagine it being a way of building a bridge. So that is maybe one thing that we have an opportunity to leverage when you do have center scale resources from the government, is that you can use that to build bridges. I don't think that we've done it as best as we could, but that's thanks for the comment, because that's a reinforces something that we've heard from other people.
I would say actually MIT is very complicated on this score. It's not, I mean, there are many cases of PhD students co-advised across department boundaries, but it tends to be in science and engineering because the money is not tied to the department. So as long as some set of PIs can agree that they want to, what happens is, someone in one department or another department, they'll come and trade off funding the student on a year-by-year basis, but they're both on the committee. Most departments at MIT are pretty flexible about faculty from outside that department being the supervisor. Not that certainly being on the committee, but even being the supervisor from outside the department. That kind of works until you get to departments where the funding is not from outside grants and it's actually from institute funds, and then it tends to be allocated to the department, and it's a complete nightmare. So the hardest places that I've been working on are things like economics and computer science, political science and computer science, totally different funding models. Like even if a CS person wanted to advise an econ or political science student, the size of their program is fixed. More money does not help people. There be more students in that area. It's a fixed size program funded centrally by the institute. So, but I don't see it as much here in within the science and engineering fields. I think there it's more a cultural issue actually than a sort of bean counting issue. I've seen places where it's a bean counting issue, but I don't think it is here.
Anything else from the room?
I was just thinking about the comment you made about physicists looking at the methods or like developing methods as their export skeptically. And that just makes me really sad because I learned probability theory not from like BDA or from McElroy, but from my favorite book, which is Jane's Probability Theory. And that's like this huge contribution from physics using fundamental science and exporting that into statistics. Really, to me, like defining the field there. I feel like if we had a physics view and how it is now, I would appreciate it better.
But your view is shared by many people. I mean, there is something about the methodologies or the principles that physics uses that you could imagine having, let's say, a PhD program built around. It happens to be that in the MIT physics department right now,
when a PhD student comes in, they're assigned to an oral exam. That oral exam is testing domain knowledge. But we're now being forced to confront this because now it's totally legitimately a conversation about hiring faculty who work on thinking of AI, ML as if it were a physical dynamical system and actually applying physics insights to understand the dynamics of those synthetic systems. And I personally, I believe that has a home in the physics department, but I have colleagues who disagree, who say that the definition of physics is the systems that you study. But I think it's a missed opportunity, and the example that he gave is a fantastic one. But again, when it comes to thinking about the structure of a graduate program, it has been question-centered more than methodologically centered. And if you can have the question be like the actual study of the physics of statistics, the physics of ML, or that is an emerging area which I think is intellectually interesting and actually quite important.
There are these institutes at Chicago and UCSD, right, where you have data science institute where physicists are part of it. It's a single institute. I think MIT should have it.
We have both, right? So MIT has the Statistics and Data Science Center, which brings people together for the. It's a different scale, and physics doesn't participate as much.
I mean, I shouldn't use because they're not really institutes there either, right? They're kind of, right? But I think if there was I think there's an opportunity for a new department, right? But I'm also too junior to say these things.
Universities have a really hard time creating departments.
I'm not.
You think it's hard? You think it's hard getting your physics colleagues to like slightly change the the qualifying exams? Because in the end, universities don't usually grow the size of the faculty much, so new department means picking up some of the slots and moving them somewhere else. It's very hard.
If you can get $1 billion and for somebody who says there should be a new department, I think this helps.
$1 billion.
Barely, actually, with $1 billion. It's kind of crazy.
Okay, so we've covered a lot of ground. So just as sort of a closing, I'd like you to all pick something as your main takeaways for us.
I'm gonna let the physicists go first.
Let's see. So, I think it's whether or not generative AI. I mean, that's the umbrella that we're brought here together under. Generative AI. This is a strategic direction coming from the president at MIT. Very important. Whether or not that is the thing that actually has an impact in physics, it is opening up a conversation about this intersection and the fact that we are having this event in the College of Computing, which has this potential to be a real bridge between disciplines and ones that we can build a common language. I think that's the start of something that could be quite exciting, but it requires fostering. And it is very easy for us to have these conversations and kind of go away and grab a snippet of information from each of the talks that we heard and kind of retreat and just use that internally as opposed to using that as a way to continue a dialogue. And so I think that kind of dialogue and especially a dialogue with junior people who are the people who are like actually wanting to go into this area, developing things, that needs to continue. And I hope for the white paper that actually some of the junior perspectives that are getting worked in there about what the impact would be, especially thinking about careers in interdisciplinary spaces, making sure that there's home for that type of research that we're trying to cultivate.
So I have an advertisement. I said that. So there's space down on the third floor of this building that we're allocating on a semester by semester basis based on proposals from groups. It has to be some computing related group that wants to that's not physically co-located today and wants to have some ideas about what they could do by spending a semester together. There's a small amount of money to like pay for some lunches and stuff, but it's mainly a space where like graduate students, postdocs don't sit together, could maybe spend a semester together, and a set of faculty could come, spend some time with that students and postdocs. So the inaugural one of those is this semester, because the building just opened in January. And that's a group of people, from, Earth, Atmospheric and Planetary Sciences, Civil Engineering and IDSS, who are looking at computing, and climate issues. And the ones for the fall, I'm pretty sure the call has come out, but I'm not totally sure, but I'll send it to Jesse.
All right, takeaway, I'll just say that there's a real opportunity to make an important and different impact to AI and other domains. And I think people need to keep this in mind, and we need to think about the uniqueness of physics problems, and how it lives in the greater AI sphere.
Sorry, I didn't do my takeaway. I did my advertisements. I didn't want people to think I was trying to get away without a takeaway, although it was. So I guess my takeaway is that, the College of Computing is trying to figure out how to foster exactly the kinds of things that we've been discussing here. I don't think we have the answers. And the answers, I think, are different in different fields, actually. That's one of the things we're discovering. So, but I do think that some mix of, research level and research and then educational things at both undergraduate and graduate level are very important. I'm a firm believer that doing some teaching together actually unlocks interesting research questions. Because you get to know people and the things that they work on. That certainly happened to me in my career. And so, I just encourage people to look for those opportunities. It really is a thing where people doing some things individually with some other people can start to actually create a movement, especially among graduate students and postdocs and young faculty. Fields change with generations. It's just kind of the way it goes.
Thank you very much. Let's thank our panel.